Okay, so let's do the last 20% of this exam. This question says, what is the conjugate base of bicarbonate HCO3-? So if we want to find the conjugate base, we want to see what we get if this acts as an acid. So I'm going to write out the reaction of bicarbonate. So there's multiple possible reactions, at least 2. But here we have our bicarbonate ion, aqueous. And we want this to act as an acid if we're looking for the conjugate base. So if this is an acid, I'm just going to react it with water plus H2O liquid. So this is going to be our base here. And then we just need to remember the role of acids versus bases in these dynamic equilibria. So what happens here? Remember, the acid is going to lose a proton, and the base is going to gain a proton. So what we're going to be left with is CO3 2-. That's going to be our conjugate base, which is what we're looking for here. And hydronium H3O+ is our conjugate acid. Okay? So our answer is this ion carbonate, CO3 2-. Essentially, if you ever want to find the conjugate base of something, just pull off an H+ and see what you get. If you ever want to find a conjugate acid of something, just add an H+, and that'll be the conjugate acid. Okay, in this problem, we're asked to relate an initial amount and an equilibrium amount. Time goes by, things change. Okay, when in doubt, we're going to ice it out. So here's our reaction, and then we're just going to write next to our reaction I for initial, C for change, and E for equilibrium. Then we're going to fill out any information we know here. So just note this is a 2-liter flask, and we're given a number of moles. So you always want to plug in either partial pressures or concentrations, not moles, into an ICE table. So let's just calculate that. So 2.06 moles of NF3 divided by 2 liters is going to be 1.03 molar. So that's what we're going to plug in for the initial concentration of NF3. We can assume, unless we're told otherwise, so we're told that we're just putting NF3 into the reaction vessel. So we can assume this is 0 and this is 0. So then plug in any other information that we have. What other information do we have here? Hark! We have the equilibrium number of moles of N2. So we're just going to divide this by, oops, that looks like a percentage sign. And divide this by 2 liters to get the molarity. So the equilibrium amount is 0.0114 molar. Okay, now we have an initial amount of this and all of this stuff, and we have an equilibrium amount. So since we know the equilibrium amount and the initial amount of the N2, we can find the change. It was plus 0.0114. And if we know the change in one thing, we know the change in everything. So for example, this over here, since the stoichiometric ratio is 1 to 3, the change would be plus 3 times 0.0114. And meanwhile, over here, the change will be minus 2 times 0.0114. Now we can find all of our equilibrium amounts. So for the NF3, it's 1.007 molar. And we'll have 0.0342 as the concentration of F2 gas. So remember, ICE tables come in 2 flavors. There's one where you have to use variables. But if you ever know, again, the initial amount and equilibrium amount of something, you can always find the change. And if you know the change in one thing, you can find the change in everything else. So this is the second flavor of ICE table where we can just plug everything in. Now, to find Kc, all we have to do is set up our equilibrium expression, which you'll notice is conveniently located right up here. And then we'll plug in the values from our equilibrium line in order to get what Kc is. So we have our N2 times our F2 concentration, 342, and remember that's cubed. And all of this is going to be divided by the NF3 concentration squared, which is just 1.007 squared. Let's see what we get. We'll get 4.5 times 10 to the negative 7th, are essentially choice C. Okay, in this question we want to find the strongest acid. Okay, so they're all carboxylic acids. So carboxylic acids are the COOH motif, which are all weak acids. But how can we make a weak acid stronger? So remember, what's going on here is, one of the ways that a carboxylic acid works is by having these two oxygens here. It helps pool electron density in this OH bond. By pulling electrons away from the hydrogen, it makes for a weaker bond, which is easier to break. So the weaker we can make this bond, the stronger our acid can become. So how can we take this bond and really polarize it? Well, by adding in really electronegative atoms. So if we were to add in, say, fluorines, for example, then just in this example alone, rather than just having a mini polarization of this bond, we get a massive downstream effect that really polarizes this bond, makes it super weak. That's a terrible looking polarization arrow. Let me try this again. It really, really polarizes this bond, which makes it really weak, which makes it really easy to break. So, in actuality, just by adding in these three fluorines, we make a carboxylic acid roughly 100,000 times stronger, which is notable. Notice that none of our answers match this one, but the idea is more electronegative atoms means more polarized bond, means a weaker bond, means a stronger acid. So of these carboxylic acids, you're looking for the one that has the most electronegative atoms added to it, which is choice D. It has a fluorine, which is more electronegative than bromine, or chlorine, or iodine, or a methyl group. So we can make this even stronger if we added in even more fluorines here, but still noticeably stronger than acetic acid. Up next, a true or false question about thermodynamics. Statement 1. Thermodynamics can tell us about the speed of a reaction. No, it can't. That's not thermodynamics. That's kinetics, which is a field that we've already studied. Kinetics can, thermo cannot. So I did not like choice 1. 2. Thermodynamics can tell us about the extent of a reaction. Yes, it tells us about the spontaneity and the extent. So this one is indeed true. The next question says if delta G standard is positive, then KEQ is greater than 1. So what does this mean? Well, KEQ and delta G standard can be related either through an equation. Delta G standard equals negative RT times natural log of K. So if we think about this, if KEQ is greater than 1, the natural log of anything greater than 1 would be negative, which means we'd have the negative... One second. Sorry, let me restart that. If KEQ is greater than 1, if products are favored, that means that the natural log of K would be positive by definition of how natural logs work. So the natural log of anything greater than 1 is a positive value. So that means if K is greater than 1, we have a positive value times a negative, which would be a negative. So this brings up an important fact about thermodynamics. If KEQ is greater than 1, which again means products are favored at equilibrium, then delta G standard is negative. This relationship here always holds true. If KEQ is greater than 1, then delta G standard is negative. That's what we see mathematically from this equation. So in terms of Statement 3, if delta G standard is positive, then KEQ is greater than 1. That's false. Okay, it's actually the opposite. If delta G standard is positive, that means that KEQ is less than 1. So what that actually means is that reactants are favored at equilibrium. If we want to picture a graph here, where we plot free energy on the y-axis and extent of reaction on the x-axis. So if delta G standard is positive, that means we're going from a lower free energy up to a higher free energy if you consider pure reactants over here and pure products over here. This sort of curve will look something like this. And remember that equilibrium is at the lowest energy point. So, if you have a positive delta G standard, so if you have a positive delta G standard, which is what we have in this situation, that means that equilibrium will favor reactants. And from a thermodynamic standpoint, that's because these are lower in energy. Lower energy means more stable. Okay? If, on the other hand, you have a negative standard free energy change of the reaction, so if we went from reactants having a higher free energy formation to products having a lower energy formation, then what we're going to notice is our curves will look like this. So if we have a negative delta G standard, that means our equilibrium is going to favor the products. Okay? So, anyway, now back to this. If Q is less than KEQ, then delta G is negative. So if Q, the product-to-reactant ratio that we have, is less than K, the product-to-reactant ratio that the reaction is eventually going to settle at, then indeed the reaction will move spontaneously forward, which means delta G would be negative. So I like this one too. So 2 and 4 only are true. The next question says, what's the best way to classify the nitrate ion, NO3-? Remember, this is the conjugate acid of HNO3, right? And HNO3 is what type of acid? Well, it is strong. Remember, by definition, a strong acid, when it goes all out. It's going to dissociate completely into H plus and NO3 minus, which means this is a negligible conjugate base. And in fact, when I write this out, I'm going to put base in quotation marks. It's the conjugate base, but this thing right here, look, it can't even grab onto a free proton to reform HNO3. If it can't do that, then there's no way it's going to be able to hydrolyze water. So the conjugate base, quote unquote, of a strong acid is a negligible conjugate base. All right? So we can call this, it would be a spectator ion in aqueous solution. It's not going to be able to hydrolyze water. And that's it for Exam 2B. Great job. Thank you for tuning in. And dominate the exam.